if you can just see the function and you can visualize the graph of it. There are some very easy and basic tricks to do that. We are going to discuss about such tricks today. So in the basic functions, we are going to discuss these many basic functions, which are the basic unit of all the functions visualization. After that, these are the some tricks 1, 2, 3, 4, 5. These 5 tricks will help us to draw uncountably many other functions. Now, okay. Then these some special functions which are a bit useful and important. And then last, how do I learn and function visualization? Let's start from some basic function. First of all, we have this identity function. We can represent it by fx equals to x. And now the graph of this goes. The graph of it is something like this. It is a straight line which passes from x-axis. And as you put the values of x input, the same value will be the output. Very easy. Then other is 2x. Whenever you have a function of this like this x to the power 2n, the graph will be always like this. When the value of x increases, it also increases, and for negative values it also goes to the infinite, positive infinite. Now as the function changes, I multiply by some number or I add some number, then the position and shape may shift a little bit, but more or less the main general shape of this type of function will be like this. Next, the polynomial function of odd power means you have x to the power 3, x to the power 5, x to the power 7 like this. So the graph of this, when x is increasing, tends to infinity, the graph will be something like this. As x goes to infinity, it goes to positive infinity, and x goes to minus infinity, it also goes to minus infinity. Again, for different things, if I add 3 or I multiply by some number, add some other number, then it may change the shape and position a little bit. More or less, general form will be like this. Then modulus function. Modulus function is how we define it like fx. If the input is greater than or equal to 0, the input remains the same. And if the input is less than 0 means negative. So it multiplies the input by a minus. And how the graph looks like? The graph is something for positive values, it remains like this. And for negative values, it is just the mirror image. So this is the graph of mod x. Then greatest integer function. What is the meaning of greatest integer function? If you you just have a number, let's say 2.65, so and you take the greatest integer function, the greatest integer available in this number is 2, है ना? The biggest number you can extract is 2. So this is the greatest integer function, and if you put an integer inside the function, it will give you same as it is. So how the graph works? So at 0 the value will be 0, and for all values till 0 it will be like this and a open here. Then at 1 the value again becomes 1. At 1.1, 1.2, 1.3, 1.4, 1.5 the output is remain 1. Then what happens to as input 2, the answer becomes 2, and 2.1, 2.2, 2.3, this value of input, the graph is like this. So you can just see this is the graph. Same thing will happen here. Empty circle means that point is not included, and dark circle means that point is included. So this is the sort of greatest integer function graph. Okay, next, what is fractional part? It is again very interesting and nice example. If you have a 2.65, let's say you input this point in fractional part of function, what will happen? It will take that point and subtract the greatest integer out of it. So it will be 0.65, है ना? So if you have any number as the input, you will just take the fractional part of that number. So how is the graph? So at 0, the answer will be 0. As you go 0.1, it will go like this. As it goes 1, the point 1 will not be included. As you input f1 here, so it will give you 1 minus 1, which means 0. So again it comes back here. Again, as you increase the value, so the value will increase. As you reach 2, it will not be included. It again becomes 0. And this process keeps going on. Same thing happens in the negative part. minus 2, this will be included, and then till minus 1 it will be empty. Minus 3 will be included, and then till minus 2 it will be empty. This is the graph of fractional part of the function. Next we have least integer function. It is just opposite of greatest integer function. So if you take 2.65, the greatest integer function was giving 2, but here what is the next integer out of it? We think it like this. The next integer is 3, है the next greater integer than this is 3. So the graph of it goes something like this. You can see the graph is like stairs. So the stairs are shift by 1 point upside. This is the difference between the least integer function and the greatest integer function. Now about exponential function. So there are two type of cases. If you have, let's say, if this a is greater than 1, so what will happen? Then the graph of this will be like this. And this point is 0, 1. Okay. And when the value of a, when the value of this a is greater than 0 and less than 1, so the graph goes something like this. This is again asymptotic, and the point is same 0, 1. So these are the graph of exponential functions. Next we have logarithmic functions. So if I am saying log a, again for this thing, if this a is 0 to 1, greater than 0 and less than 1, the base, so the graph will be something like this. And the point, this special point is 1, 0. And if in the same case, if I have the value of a, this base value is greater than 1, so the graph will be like this. It will start from here, it cut this point and goes like this. So again this point is 1, 0. This is the graph of logarithmic function. So how the signum function works? The graph of signum function, the function is defined something like this. If x is greater than 0, then the output will be 1. If input is 0, the output will be 0. If the input is less than 0, means negative, then the output will be minus 1. So the graph goes like this. It is 1, it is minus 1, and it is 0. So at 0 the output is 0, dark circle. For all values greater than 0, it will be something, a straight line, and for input as negative on the left side, it will be for all values the answer will be minus 1. This is the graph of signum function. Next, now we are talking about some trigonometric functions. So trigonometric functions are periodic. So how the graph of sine goes? Its upper value is 1, its lowest value is minus 1. The graph will be something like this. At 0 it becomes 0, at pi by 2 it becomes 1, then at pi it becomes 0, then at 3 pi by 2 it becomes minus 1. Same thing happens on this side. At minus pi it becomes 0, at minus 3 pi by it becomes 0, and it keeps continuing. This is the graph of sine. Now let's talk about the graph of cos x. So the graph of cos x is something like this. At 0 the answer is 1, and at pi by 2 the answer is 0, at cos pi is minus 1, cos 3 pi by 2 is again 0, and it goes like this. On left side, cos minus pi by 2 is 0, cos minus pi is minus 1, and cos minus 3 pi by 2 is 0, and then it goes upside. This is the graph of cos x. Now let's see the graph of tan x. So at 0 it becomes 0, as tan pi by 2 goes to infinite. So the thing will go like this. Tan minus pi by 2 goes towards minus infinite. Now, and there is a asymptote at pi by 2. Means it will not touch this line. It will go closer and closer and closer and closer. Same thing will happen at minus pi by 2. It will go closer, but it will never touch. So this is one branch only. The second branch of tan x goes something like this. At 3 pi by 2 again we have a asymptote. And same thing will happen here this side. minus pi by 2 0, and then the graph goes like this. At minus 3 pi by 2 we again have a asymptote. Okay, this is the graph of 10x. Now let's talk about cortex. The graph of cortex goes like this. At pi by 2 it becomes 0, and then it has an asymptote at pi. Asymptote means the graph function will go closer and closer, but it will never touch that line. Now then the next line, same thing will happen on this side. Minus pi, again we have a asymptotical line. So it will not touch the function, but it will go closer and closer. And same thing happen here. So this is the graph of cortex. For graph of secant, we have to first observe the graph of sin cos. And the graph of cos was like this. So now the graph of sec is related. We know sec x is 1 upon cos x. So the graph is also related. How is the graph? It is go just opposite directions. The green one is the graph of sec x. For the graph of cos x, we will need the graph of sin x. So the graph of sin x was something like this. Okay, so we know that cosec x is equals to 1 upon sin x. So this will happen here just opposite of the sin x graph. The green one represents the cosec x graph. Like this. Now let's talk about some inverse trigonometric functions. Let's talk first about sin inverse x. The domain of sin is minus 1 to 1, and the range of sin x is minus pi by 2 to pi by 2. The graph of sin inverse x will be like this, starting from here, here, and like this. This is the graph of sin inverse x. The domain of cos inverse x is minus 1 to 1, and the range is 0 to pi. So the graph of cos inverse x is like this. This point is pi by 2. Domain of tan inverse x is real number, and the range of tan inverse x is open bracket minus pi by 2 to pi by 2. And the graph of this is like this. The domain of cot inverse x is real numbers, and the range of cot inverse x is 0 to pi. The graph of cot inverse x is like this. Second last inverse trigonometric function is sec inverse x. The domain of sec inverse x is real numbers except minus 1 and 1, this range, this interval, and the range of this function is 0 to pi, but just remove one point, that is pi by 2. So it will be something like 0 to pi minus 1 to 1, removing this area. There will be a asymptotic line at pi by 2. This is not included in the range. So there will be asymptotic line here, and the graph of sec inverse x will be like this. It starts from minus 1 and it will go like this, and it will start from 1 and it will go like this. So the green color is showing the graph of sec inverse x. The domain of cosec inverse x graph is again set of real numbers minus this interval minus 1 to 1, and its range is the interval minus pi by 2 to pi by 2, but remove one element, that is 0. The graph of cos x will, you see, minus 1 to 1. So it should not be in this domain, and everything is going to work between pi by 2 and minus pi by 2. 0 is not included. The graph of this will be something like this. 0 will be the asymptotic line here, and same thing will happen here. These are the graph of cosec inverse x. Now there is a relation between the graph of sec inverse x, inverse trigonometric function and trigonometric functions. So what is the relation? So the trigonometric function, I'll say inverse trigonometric functions are mirror image of trigonometric functions with respect to what? With respect to y equals to x. If you just take the y equals to x line as a mirror and you reflect the graph of trigonometric functions, you will get the graph of inverse trigonometric functions. You can also try it. Now I'll tell you how you can draw infinitely many and countably many graphs by just these basic tricks and the formulas. Okay, number one is fx plus minus ax. If you have the function and you just add or subtract something into it, so what will happen? I am taking an example of x square. So the graph of original x square is something like this. Now I am drawing the graph of x square plus 2. So what will happen? The graph will shift 2 points upwards as it is. And you can also think what will happen if I just draw the graph of x square minus 2. The graph original from the green, the original graph will shift 2 points downwards. Here I am adding a number in the input. So again I am taking the example of x square. If the graph of x square is like this, okay, now I am adding in its input. I am adding in its input means I am making it x plus 2. I am adding here. So what will happen when you will add some number into the input? So what will happen? It will go towards left 2 points and the graph will be like this. Same graph just shifted left side. And if you instead of adding, you just subtract from the input any number, so the overall graph will shift towards the right side. Okay. Trick next. If you multiply any number by the function, output of function, this time I am taking an example of fx equals to sin x. Now what will happen if I multiply the whole thing by a constant which is greater than 1? So I am making a new function fx equals to 2 multiply sin x. So what will happen? First of all, the things will go to 2. At 0 it will remain the same. So it will go something like this. You can see what is happening here. It will go bigger. All the values of output will be doubled, hai na? So in terms of y-axis, the x-axis remains the same, but in terms of y-axis, the graph is shifted to, it extended in both the sides. Now if the same thing happens, if I multiply a constant inside, so if the original function is sin x, so here I am changing the input, the changes will occur on the x-axis. If I am just doing sin 2x, now I am multiplying by a number greater than 1 to the input. So what will happen? Now this will shrink faster. So the graph will be something like this. I did a mistake, and the mistake is this. This is not the graph of sine. I worked for the graph of cos. This is the graph of cos x, and the resulting graph is of again cos 2x. So this will happen for the graph. You can see it just shrink towards the y-axis. If you multiply a function by minus, what will happen? So let's say I am taking an example of, let's say this time fx as a to the power x. So the graph was like, this was the graph of a to the power x. If I multiply it by minus, means I want to draw the graph of minus a to the power x. So it will make an mirror image with respect to x-axis. So the new graph will be like this. This is the graph of minus a to the power x. Okay. Now, second part of the trick, if I multiplied by the input by -1, if the original graph is, again I am taking the exponential example, a to the power x, the graph was like this. What will happen if I multiply by minus 1 to the input, a to the power minus x? What will happen? Now it will be mirror imaged with respect to the y-axis. There it was with respect to x-axis. It is a to the power minus x, and this is a to the power x. So this is the trick. Next, now it is just combination of both of these. What will happen if I multiply the input as well as the output? Okay, so I'll do it in 3 steps. First of all, I'm taking a to the power x. This is the graph of a to the power x. Now I'll multiply it by the input, negative. So I'll make a to the power minus x. What will happen a to the power minus x? The graph will be this one. This is the graph of a to the power minus x. Now in the third case, I'll multiply the resultant by minus again. So when I multiplied the output, the complete graph, it gives me an mirror image with respect to x-axis. So the graph will be like this. Now I mirror image the blue color function. This is the new function of minus a to the power minus x. So just repeat, if you have a function and you do the mod, again you are doing the modulus of output function. So what will happen? Now let me take the function as fx equals to sine x. What will happen if you take the modulus of this function? Means whatever is the function, you take the modulus of output. So what it will do, it will make everything as positive. The green function will represent this negative term will again also become the positive will remain the same, negative will become the positive, and then positive will remain the same. So the green function represents sine x modulus, and then the red function represents the sine x only. So this is happening when I am taking modulus of output. Second part of this trick, when I take the modulus of input, let's say my function is again fx is sine x, modulus of fx, modulus of sine x. This green color graph is representing the sine mod x, and the red color graph, let me draw it complete. The red color graph is representing the sine x graph only. Now what will happen to 1 upon fx? Let's say fx is x square. So the graph was like this. And I want to take it 1 upon x square. So when it was 0, the function will become infinite. And when it was going towards infinite, the function will go towards the 0. Just the opposite, because we know that 1 upon 0 is infinite and 1 upon infinite is 0. You will treat the function as like this. Now let's talk about some other important and very interesting functions. One such function is sine x multiply sine inverse x. You know the graph of sine x, but when you multiply it by minus 1, the graph becomes like this. The bigger the value of x, it will increase the value of sine in the same order. So the waves of sine, they expand according to the value of x. Next very interesting graph is x plus sine x. But when you do x plus sine x, the graph will be like this. Next graph is 1 upon sine x, one of very interesting graphs. Again, let me draw the graph of sine x first. The graph of sine x is like this, and the graph of sine 1 upon x will be something like this. It will remain okay outside, but as it come closer to x-axis, the waves become very tight, and as you go far, the waves starts becoming normal. Okay, and what will happen now? I just wanted to show how the sine x multiply sine inverse x function work. You know how the sine 1 upon x function work. You can use these two tricks and you know how the x multiply sine 1 by x function will work. So the sine in 1 by x function make the waves very close to each other when it is 0, and when you multiply by x, it increase the size of waves. So by adding these two tricks, you can see, and nearby the graph will be something like this, because it is the graph of sine 1 by x, and as you multiply by x the whole function, the size of wave will increase according to the value of x. So now about me, how I learn and practice visualizing functions. For this, I use GeoGebra. You can go to the website of GeoGebra and you can directly start the calculator. You can also download the software in your laptop, and the app is also available in Play Store. Okay, now at the end, we are doing the complete reanalysis playlist. You can see all the videos. We have a Telegram channel. You can like, comment, and subscribe if you want. And please share the video with all your friends so that more people can be benefited. Thank you very much. Bye, Tata.